Coal has the potential to revolutionize microelectronics, leading to significant advancements in this field. Greetings to everyone. In today's video, we will be exploring the groundbreaking work of researchers from the University of Illinois Urbana-Champaign, the National Energy Technology Laboratory, Oak Ridge National Laboratory, and the Taiwan Semiconductor Manufacturing Company. They have successfully devised a method to transform coal char into nanoscale carbon disks known as carbon dots. These dots can be interconnected to create ultra-thin membranes for use in two-dimensional transistors and memristors. Unlike other carbon layers, those derived from coal do not contain any dangling bonds, which are unattached electrons that can impede the movement of charges and hinder transistor switching speed. The team is currently focused on developing a fabrication process that can be implemented in industrial settings for coal-based carbon insulators. Without further delay, let us now delve into our in-depth discussion. In the United States, coal is a plentiful resource that, regrettably, has played a part in climate change due to its utilization as a fossil fuel. As the nation shifts towards alternative methods of energy generation, it becomes crucial to assess and reassess the economic significance of coal. A collaborative study conducted by the University of Illinois Urbana-Champaign, the National Energy Technology Laboratory, Oak Ridge National Laboratory, and the Taiwan Semiconductor Manufacturing Company has revealed the potential of coal in powering advanced electronic devices of the future. According to Ching Tao, a professor of materials science and engineering at the University of Illinois and one of the key contributors to the project, coal is typically associated with being bulky and dirty. However, through our innovative processing techniques, we have successfully transformed it into ultra-thin, high-purity materials at the atomic level. The distinctive atomic structures and properties possessed by these materials make them exceptionally suitable for producing highly advanced electronics that surpass the capabilities of current technology. The NETL has pioneered a process that converts coal char into nanoscale carbon disks known as carbon dots. These dots, as demonstrated by the U of I research group, can be interconnected to create atomically thin membranes. These membranes have wide-ranging applications in two-dimensional transistors and memristors, both of which are crucial technologies for the development of more advanced electronics. The journal Communications Engineering has published these findings. As we continue our quest for electronics that are smaller, faster, and more efficient, the ultimate breakthrough will involve creating devices using materials that are only a single or double atom thick. Devices cannot be smaller than this limit, and their compact size often results in faster operation and significantly reduced energy consumption. Extensive research has been conducted on ultra-thin semiconductors. However, in order to successfully build functional electronic devices such as transistors and memristors, it is equally important to have insulators that are atomically thin and capable of blocking electric currents. Two-dimensional devices can benefit greatly from the use of carbon layers that are atomically thin and possess disordered atomic structures, as they exhibit exceptional insulating properties. Through their collaborative efforts, the researchers have successfully demonstrated the formation of carbon layers using carbon dots sourced from coal char. In order to showcase their abilities, Cao and the U of I team successfully created two instances of two-dimensional devices. This is truly exhilarating because it marks a groundbreaking connection between coal, typically associated with low-tech applications, and the forefront of microelectronics, remarked Cao. In their research, Chao's team harnessed carbon layers derived from coal as the gate dielectric in two-dimensional transistors constructed using either the semi-metal graphene or the semiconductor molybdenum disulfide. This innovative approach resulted in a remarkable enhancement of device operating speed, surpassing previous benchmarks by more than twofold, while simultaneously reducing energy consumption. Similar to other materials that are atomically thin, the carbon layers derived from coal lack dangling bonds, which refers to electrons that are not bonded chemically. The electrical properties of conventional three-dimensional insulators are altered by the abundance of these sites on their surface, as they effectively act as traps that hinder the movement of mobile charges and subsequently slow down the speed at which transistors switch. In contrast to other materials that are atomically thin, the carbon layers derived from coal are amorphous, lacking a regular crystalline structure. In order to prevent leakage, which refers to the undesired flow of electrical currents through the insulator and the subsequent increase in power consumption during device operations, these materials lack boundaries between distinct crystalline regions that act as conduction pathways. Additionally, Chow's research group also explored the potential use of these materials in memristors, electronic components that can store and manipulate data, thereby greatly improving the functionality of AI technology. By utilizing electrochemical reactions between a pair of electrodes with an insulator sandwiched in between, these devices have the capability to store and represent data through the modulation of a conductive filament. Through their research, the scientists discovered that by utilizing ultra-thin coal-derived carbon layers as insulators, it becomes possible to rapidly form filaments with minimal energy consumption, resulting in high device operating speeds and low power requirements. In addition, the coal-derived carbon layers contain atomic size rings that confine the filament, leading to improved reproducible device operations that enhance data storage fidelity and reliability. The Chow Group's innovative devices serve as evidence that coal-derived carbon layers can be successfully utilized in two-dimensional devices, demonstrating a proof of principle. The next step is to demonstrate the feasibility of producing such devices in large quantities. Chow expressed the semiconductor industry's keen interest in the potential of two-dimensional devices, along with our partners at Taiwan Semiconductor. Our goal is to deliver on this promise by working closely with NETL to establish a manufacturing method for carbon insulators derived from coal. This process will be specifically designed for application in industrial environments, and the University of Illinois will remain committed to this collaboration in the coming years. To support our channel's growth and ensure broader awareness, kindly hit the like and subscribe buttons. This will help us reach more individuals and disseminate valuable information. Thank you in advance.